Hello my dear students, welcome to my channel Is Educare. Today I am going to discuss the first chapter, real numbers. Already you have learned in lower classes about the different type of numbers like natural numbers, whole numbers, integers, rational and irrational. All these numbers, rational and irrational, and under them have these numbers, natural numbers, whole numbers, integers, are real numbers. So in this chapter we have some important terms like lemma, algorithm, and then important algorithm, Euclid's division algorithm. So let us know these terms, lemma, algorithm and Euclid's division algorithm. Lemma. So what is lemma? A lemma is a proven statement which can be used to prove another statement. So remember, a lemma is a proven statement which can be used to prove another statement. Then algorithm. What is algorithm? An algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. So, an algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. So, remember these two terms. Then we have Euclid's division lemma. Now, what is Euclid's division lemma? If A and B are two positive integers, then there exist unique integers Q and R satisfying A is equal BQ plus R, where 0 less than equal R, R less than B. Now this Euclid's division lemma is nothing but the relation of dividend, divisor, quotient and the remainder, which already we have learned in lower classes. So to understand this, let us take an example. Suppose if we divide 17 by 3, what we get? This is 3 5 ja 15 and left remainder is 2. Now what is the relation? 17 is equal, divisor is 3 into is 5 plus remainder 2. Now this remainder is less than this 3. So here remainder is 2 and the divisor is 3. So remainder is always less than the divisor. Okay? Or remainder may be 0 also. Here written 0 less than equal the remainder may be 0 also, and it is less than what? B. B is the divisor here. So this Euclid's division lemma is same as this relation. So remember this. Now using Euclid's division algorithm, we solve some problems we have in exercise 1.1 and some proof will do, and some extra questions from other books we'll discuss. So let us start with exercise 1.1. So first question, what we have? First question we have, use Euclid's division algorithm to find the HCF of. First question, 135 and 225. So given integers, solution, given integers are 135 and 225. 135 less than 225. Applying Euclid's division algorithm, to 135 and 225, we have 225 is equal 135 into 1 plus. So you do like this, 225 divided by 135, it is 1 time, and 135 you subtract. 5 minus 5, 0, 12 minus 3. What is 12 minus 3? 9. So this is remainder, here it is the remainder. Then you see the remainder not equal 0, since R means remainder not equal 0, applying Euclid's division lemma to 135 and 90. What we get? 135 is equal 90 plus how much? Again you see this, we divide 135 by 90 one time, is 90 left. If you subtract, you will get 45. So later on again we will divide the number, that is 90. So 45 to the 90. So like this. So 90 plus what is remainder? 45. Here 90 into 1. 90 into 1 plus 45. Since R not is equal 0, apply Euclid's division lemma to 90 and 45. We have 90 is equal 45 into 2 plus 0. Since remainder, that is R is equal 0, therefore HCF of what numbers? We have 135 and 225 is the last remainder, that is last remainder 0. Before that we have 45, so this 45 is the HCF. So remember this. This is the last divisor, that is last, the divisor is 45, by which we divide 90, that is the what? HCF. Question number 1, 2. So this time we have 196 and 38220. So here 196 less than 38220. By applying Euclid's division algorithm, we get 38220 220 is equal 196. Now we divide this 38220 by 196. First, if we take this 2 times, it will be more than 382, so it will be 1 time. 196. So 12 minus 6, 6. Here left 7, 17 minus 9. How much? 8. Here left 2, 2 minus 1, 1. And this again bring 2. Again this time, how much or how many times of 196 is 1862 or less. So by observing this, if we take, it will be almost 9 times. We take 9, or you will calculate 9 6 is 54, carry 5, 981, 586, carry 8, then 9 8 17, and subtract. So 12 minus 4, 8. Here left 5, so 15 minus 6, 9. Then this is 9 8, then this being 0. Now how many times of 196 is 980? So almost you take different numbers and multiply this to get this. So it will be 5 times 5 6 is 30, it is 0, so 5. 5 6 is 30, 0, carry 3, 5 9 is 45, 3 48, carry 4, 5 plus 4 9. So 196 into 195 and the remainder 0. Since r is equal 0, therefore HCF, direct you can write HCF of what number? 196 and 38220 is equal 196. So this is the divisor. So this is the HCF here. Next, question number 3. 3. Given numbers are what? 867 and 255. So these are two given numbers, 867 and 255. Here 867 greater than 255 by applying Euclid's division algorithm, we get 867 is equal 255. Now we divide 867 by 255. How many times of this will be this? If we take 3 times, 3 5 is 15, 15 1 16, then 3 2 is 6 1 7. So this will be 3 times. 3 5 is 15 5, carry 1, then 15 1 16 6, carry 1, 3 2 is 6 1 7. Subtract this. 7 minus 5 2, 6 minus 6 0, this 8 minus 7 1. Now we divide this 255 by 102. 255 by 102, so it will be 2 times. 2 to the 4, 2 to the 0 is 0, 2 and the 2. So subtract this. 5 minus 4 1, this is 51. Again we divide this 102 by 51, so this will be 2 times. So 2 0 1 here, remainder 0. So 255 into 3 plus remainder 102. Since next what we take? 255 is equal 102 into 2 plus remainder 51. Next 102 is equal 51 into 2 plus remainder 0. So last divisor is 51, then or non-zero remainder is 51. Therefore HCF of what numbers? 867 and 255 is equal 51. Next exercise question number 2. So that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. So what we have? Positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5. So question number 2. Let A be any positive integer, and b is equal 6. Then q and r are unique integers such that A is equal 6q plus r, where what we have? 0 less than equal r less than 6 by Euclid's division lemma. Then what are the possible values of r? That is, r is equal 0, 1, 2, 3, 4 or 5. Any one of these possible. Therefore A is equal, when we take r is equal 0, A is equal how much we get? 6q. Or A is equal, when we take r is equal 1, we get 6q plus 1. A is equal, or A is equal 6q plus 2, when we take r is equal 2. Or r is equal 6q plus 3. Or A is equal 6q plus 4, or A is equal 6q plus what? 5. Since 6q plus 2, 6q plus 4 are even integers. And we know integers are either odd or even. Therefore 6q plus 1, 6q plus 3 and 6q plus 5 are odd. Hence every positive integer is of the form 6q plus 1 or 6q plus 3 or what? 6q plus 5. So next question 3, and army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? Now you see in this question, the maximum number of columns is the ACF of 616 and 32. So what we write? The maximum. I write the answer only. The maximum number of columns. Maximum number of what? Columns is the ACF of what numbers we have? 616 and 32. By applying Euclid's division algorithm to 616 and 32, we have what we get? 616 is equal 32. So how do you find this? 32, you divide 616 by 32. So this will be 1 time 2, 32, 11 minus 2, 9. Here we have 5 minus 3, 2, then 6. So what we get? How many times of this will be this? Now it will be 9 times. You see, 9 to the 18, carry 1, 9 to the 27, 1, 28. So subtract, then 16 minus 8, 8, then here left no more, so 8. You divide 32 by 8, what you get? 8 4 32, remainder 0. So what you get? 32 into 19 plus remainder is 8. Then 32 is equal 8 into 4, remainder 0. Therefore HCF of 616 and 32 is equal, last remainder, non-zero remainder is 8, or this divisor, last divisor is 8, so this is 8. Therefore the required, what did we write? Maximum number of columns. Required maximum number of columns is 8. So this is the answer. So question number 4. What we have in this, use Euclid's division lemma to show that the square of any positive integer is either of the form threesome or threesome plus 1. Square of any positive integer is either of the form threesome or threesome plus 1. So let A be any positive integer and B is equal 3. By using Euclid's division lemma, we get A is equal 3Q plus R, where 0 less than equal R, R less than 3, and Q and R are integers. Q not is equal 0. Q not is equal 0. That is, how much we get R? What are the values of R? That is, R is equal, we get 0 or 1 or 2. Squaring A is equal 3Q plus R, we get A square is equal 3Q plus R whole square is equal to 9Q square plus 2 into 3Q into R plus R square is equal 9Q square plus 6Q plus R square. Then we take different values of R. So when R is equal 0, A square is equal, what we get? 9Q square, because these two terms here left QR, two terms 6QR and R square will be 0, so this only is equal 3 into thrice Q square is equal thrice M, where M is equal thrice Q square for some integer M. When R is equal 1, A square is equal 9Q square plus 6Q into 1 plus 1 square is equal 9Q square plus 6Q plus 1 is equal 3 whole into thrice Q square plus twice Q plus 1 is equal thrice M plus 1, where M is equal thrice Q square plus twice Q for some integer M. Next, when R is equal to A square is equal 9Q square plus 6Q into 2 plus 2 square is equal 9Q square plus 12Q plus 4 is equal 9Q square plus 12Q plus 3 plus 1 is equal 3 common from these 3 terms. What is left? 3Q square. From this, if we take 3 common, we have 4Q plus here 1, and this is 1 is equal thrice M plus 1, where M is equal thrice Q square plus 4Q plus 1 for some integer M. So from these 3, what we have seen, therefore what we have in the question, square. So we have taken square, the square of any positive integer. Therefore the square of any positive integer is of the form thrice M or thrice M plus 1. Question number 5. What we have, use Euclid's division lemma to show that the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. Let a be any positive integer and b is equal 3, then there exists unique integers q and r such that a is equal 3q plus r, where 0 less than equal r less than what? 3. Now, what are the values of r? That is, r is equal 0, 1 or 2 or 2. Now we take cube of this number, a is equal 3q plus r. So here we have used Euclid's division lemma. This is Euclid's division lemma. Cubing a is equal 3q plus r. We get a cube is equal 3q plus r whole cube. Now we expand this. So a cube form a cube plus 3a square b plus 3a b square plus b cube. So in this form we have written. So now we get this is 27 q cube plus this will be also 27 q square r plus this will be 9 q r square and r cube. So case 1, when r is equal 0, a cube is equal, you see here r0, this is 0 and so this term is q, 9q r square r cube. So this term 0, this term 0, this term 0, left is 27 q cube is equal, this can be written as 9 into 3 q cube is equal 9 m, where m is equal thrice q cube for some integer m. Okay, next case 2, when r is equal 1, then a cube is equal 27 q cube plus 27 q square into 1 plus 9 q into 1 square plus 1 cube is equal 27 q cube plus 27 q square plus 9q plus 1. From the first three terms we take 9 common, then we have 3q cube plus 3q square plus q plus 1 is equal 9m plus 1, where m is equal thrice q cube plus thrice q square plus q for some integer m. Then case 3, when r is equal to a cube is equal 27q cube plus 27 q square into 2 plus 9 q into 2 square plus 2 cube is equal 27 q cube plus 27 into 2 54 q square plus 2 to the 4 9 is 36 q plus 8. Now from the first three terms again we can take 9 common. What is having this? So in this 3q cube plus 9 6 is 54 plus 9 4 is 36, so plus 8 is equal 9m plus 8, where m is equal 3q cube plus 6q square plus 4q for some integer m. So we see that in the first case a cube is equal what? 9m. In the second case a cube is equal 9m plus 1, and in the third case when r is equal to a cube is equal in the form 9m plus 8. Therefore the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8.